All right, hello everyone. This is going to be the Chapter 2 review. So we're going to go over each section separately. We're going to talk about just the key important factors to remember from each section, and then we're going to do a number of practice problems as well that you will end up seeing very similar questions to in your quiz and your test. All right, so starting with section 1, we have that just the important points of section 2.1 here was that the x-intercept is where a graph intersects the x-axis. So an example, this will be seen as x equals 3 or 3, 0. So if on your test it says find the x-axis, and if it gives you like a suggestion there where it says x equals and then there's a box, you'll just fill in whatever number it is. So you would say like 3, 5, any number. But technically the way that we would write an x-intercept would be 3, 0, since that means that our x-coordinate is 3 and our y-coordinate is 0. Same thing goes for our y-intercept. So the y-intercept is where a graph intersects the y-axis. And so an example will be seen as y equals 2, or in other cases it will be 0, 2. But if in the case that you see in my MATLAB, it says x or y is equal and then this box, you just fill in whatever number it is. You don't have to write 3, 0 or like 0, 3 or anything along those lines. You just need to write the actual number. All right, so we have example 1 here, and we want to find the x and y intercepts, and then we're also going to graph the equation y equals 1/2 times x squared minus 8. So to find, zoom in here, let's start with our y-intercept. So to find our y, and I'm going to write y int as a short way of writing intercept. So to find our y int, we're going to set x equal to 0 and solve for y. So in this case, since our equation is y is equal to 1/2 times x squared, and since we're setting x equal to 0, this will be 0 squared minus 8. This is going to give us y is equal to 1/2 times 0, which is just going to be 0 minus 8. So we get that y is equal to -8. So that's our y-intercept. Now we want to find our x-intercept. So to find our x-intercept, we're going to set y equal to 0 and solve for x. So in this case, if we set y equal to 0, we're going to end up having 0 is equal to 1/2 x squared minus 8. So we're going to add 8 on both sides. We're going to take these over here so we have a little bit more room. And we're going to get 1/2 x squared is equal to 8. Now we have this 1/2, which we want to get rid of, so we're going to multiply each side here by 2. Those will cancel our values there, and we get x squared is equal to 16. Now we just have to take the square root of both sides, so we isolate x. And we get that x is equal to the positive and negative 4. So this means -4 and 4. All right, so we found our y-intercept, and it turns out that we have 2 x-intercepts. And this makes sense because since we have y equals some variation of x squared, this means we're going to have a parabola or a U-shaped graph. So we can start by graphing our intercepts. It's always a very important part, so let's do that first. So let's pick red here. So if we want to graph our y-intercept, we know that y is equal to -8, and we see -8 there, so we'll put a point there. then we know that our x-intercepts are going to be negative and positive 4. So we can fill in those spots, negative and positive 4. So we can pretty much guess the general shape of a parabola, and so we can just connect each one of these dots with a smooth curve. But let's just find 2 more values to get a better idea. So let's do -2 and +2. And if you notice, since x is squared, we can just put in maybe a +2, and we know that a -2 squared is going to be equal to the same value. So let's plug in 2 for x. So if we do that, then we get y is equal to 1/2 times 2 squared minus 8. So we know that 2 squared is going to be 4. So 1/2 times 4 minus 8. 1/2 times 4 is going to be 2. So we get that y is going to be equal to -6. And we see that it is going to be the same thing. So same for -2. Since if we plug in -2 squared will be 4, 1/4 is 2, minus 8 is going to be -6. So we have the same values, so let's just plot those points, and then we can call it a day. So if we have +2 and -2 values of x, and our y value is going to be -6, so we can plot some points right there. So now is when we can connect our smooth curve here. And we know that it should have a similar shape to a parabola since it's x squared. So we can just connect the dots. Oh, I missed that one. So it's going to curve up and out like this. So your graph will end up looking something along those lines. All right, so that finishes up example 1 here. So this is when we're looking at x and y intercepts and also graphing an equation, specifically a parabola. I did not mention this in the beginning, but I think it would be very beneficial to you if when watching this video, you maybe pause at certain points and try and work out these problems on your own to just see if you are theoretically ready for your quiz or test. All right, so let's do example 2. We want to determine whether 2, 1 is a solution of x plus 2 squared plus y minus 3 squared equal to 20. And then what about 3 and -2? So let's start with 2, 1 first. So we see that 2, 1, this means that x is equal to 2 and y is equal to 1. And if we just want to make sure it's a solution or check if it's a solution, all we need to do is plug in these x and y values and just see if it equals, in this case, 20. So let's just plug in these values. For x, we have 2, so this will be 2 plus 2 squared plus y minus 3 squared, so 1 minus 3 squared. And we're seeing if it's equal to 20. So now we can continue computing our equation here. So we have 2 plus 2 is going to be 4 squared plus 1 minus 3, that's going to be -2 squared equal to 20. So 4 squared is going to be equal to 16. -2 squared is going to be equal to 4. And that is all going to be equal to 20. We see that 16 plus 4, that is equal to 20. So we have confirmed 20 is equal to 20. So 2, 1 is a solution. I'm going to write it right up here. 2, 1 is a solution. Now we also want to check 3, negative 2. So we're going to do the same thing as we did before. So if we have 3, negative 2, we know that this means that x is equal to 3 and y is going to be equal to negative 2. And we're going to do the exact same thing as we did before. So we're going to take 3 plus 2 squared plus negative 2 minus 3 squared, and we're going to set that equal to 20. And now we just need to compute. So we know 3 plus 2 is going to be equal to 5, so it's 5 squared, plus negative 2 minus 3, well, that's going to be negative 5 squared, equal to 20. So we know 5 squared, negative 5 squared, they're both going to be 25. So we're going to get 25 plus 25, set equal to 20. We see that 25 plus 25 is going to be equal to 50, which we see is not equal to 20. So we would say that 3, negative 2 is not a solution. So when checking to see if something is a solution, it will normally give you some sort of expression equal to a constant. So then what you're doing is that you're replacing your variables with whatever numbers that you were given, and then you just check to see if they're equal. If they're equal, it is a solution, and if it's not, then it's not a solution. And there can be any number of solutions. So just because they give you one solution, or maybe they ask for 2, that means that those 2 can also be solutions, because there's an infinite number of solutions for equations. All right, on to example 3 here. So all we're going to do is graph our linear equation, 3x minus 2y is equal to 6. So our equation here we see is in standard form, and what we want to do whenever we want to graph really anything is we want to solve for our intercepts first. So let's solve our intercepts first. And let's write first in here. So let's start with our y-intercept. So remember, with our y-intercept, we're going to set x equal to 0, and then we're going to solve for y. So if we do that, we're going to get 3 times 0 minus 2y is equal to 6. That's just going to become 0, so we're going to get negative 2y is equal to 6. And then we just want to divide by negative 2. So we're going to get y is equal to negative 3. Now we want to solve for our x-intercept as well. And then we're going to do the same thing but flip. So we're going to set y equal to 0, and we're going to solve for x. So in this case, we get 3x minus 2 times 0 is equal to 6. This just means 3x is equal to 6 since 2 times 0 is 0. And let's just continue right up here. So we're going to divide by 3 on both sides. We're going to get that x is equal to 2. So all this question is asking us is to just graph the linear equation. And the key word here is linear. So we found our y-intercept and our x-intercept. So let's plot those points and then think about what our graph could look like. So we know our y-intercept is at negative 3, and our x-intercept is at 2. So we have 2 points here. We know our equation is linear because our question says graph the linear equation, which means that it's going to be in a straight line. And our straight line is going to have to include our x-intercept and our y-intercept. So while you can go ahead and find other values, in this case, you can definitely find other x and y values, maybe plot more points to get a better idea. But since we know it's a linear equation, both these points have to be included, we can just draw a line straight through these points, and that will be our linear equation. So we can just go something like this and pretend that that went through. It was very close. So our graph's going to look something like this, but straight. And that would be our linear equation of 3x minus 2y is equal to 6. All right, moving on, we have example 4, which is also just numbers 49, 50, and 51 in your book. So we see here this is going to be a business-oriented problem. So we see the graph below gives the annual per person retail availability of beef, chicken, and pork in pounds from 2001 to 2010. Use the graph to answer the following questions. So we see number 49 here is asking us, what is the approximate annual per person retail availability of beef, chicken, and pork in 2010? So this is asking us about a specific year. And we see that our year, or our years, are here in our x-axis, and our pounds is going to be in the y-axis, or the annual per person retail availability is our y-axis. So if we're asking about what is the approximate annual per person retail availability of beef, chicken, and pork in 2010, the only year that we have to worry about on this graph is 2010. So let's just highlight. I forget that it doesn't want to highlight that way. So highlight our year 2010 here. So that very last line we see is the year 2010, and we're really only concerned with these points that are on the line that corresponds to 2010. And this is 49, so we'll write 49. So, and we want to know the approximate annual per person retail availability for all three meats here. So let's just write them out. We have chicken, beef, and pork. And we want to approximate these values. So what we can do is we see pork here. Let's zoom in. We see pork, and it's some value over here, and it's kind of far away from our numbers on our axis, so let's make it a little bit easier. And we can draw as straight as we possibly can. It was like fairly straight. So we can draw as straight as we can, and we can do that for now, each one of these. So let's do this for beef as well. It looks like it's really close here to this line. And also for chicken. And we see that we end at this value. So we just draw this line straight through. So we see we have a mark here and a mark right about there. All right, so we made our points. And all we're doing is finding the approximate retail availability of each one of these meats. So if we're approximating, let's draw our little curvy equal signs. This just means we're approximating. So let's start with chicken. We see here that it looks like every 2 lines is 10 pounds. So every line in between is going to be the 5-pound marker. So let's start at the bottom, which coincidentally is also the bottom of our list. So we're going to start with pork. And we see here that it's pretty much halfway, but it's below 50. Just that last line there. So we know that we're looking between 45 and 50. So if we're thinking about between 45 and 50, and it looks really close to the middle, any number either, whether it be 47 or 48, 47.5, anything around those numbers are going to be pretty accurate since we're just approximating. So let's say it's 47.5. Let's just round up. So we can say it's probably about 48 pounds. Then we want to look at beef. And it looks like it is very close to actually being on that line, but maybe not quite. So let's say beef is 59 pounds. If you went ahead and guessed that it was 60 pounds, that's also like really, really close. And we're just approximating, so 60 pounds would also be a correct answer. Now we think about our last one, which is chicken. And it looks like our final notch is just below 85, but a little bit higher than the middle. So let's go with 83 pounds. So now we've approximated each one of these, which we were able to do because we have this graph. Now we want to go on to our next problem, which is 50. So we want to know in what year was annual availability for beef the highest. So in this case, we're only paying attention to our middle graph here, beef. And we want to know when it's the highest. So we're looking for the highest point on the beef graph. So it looks like our highest point here is going to be at 2002. Looks like this is our highest point. So we want to know in what year was our annual availability for beef the highest. We're going to say 2002. Now for 51, we want to know in what year was annual availability for chicken the lowest. So we're going to look for the lowest value of chicken, and well, it looks like the very first value of chicken is going to be the lowest, which corresponds to the year, which is not marked, but we see that every other line is marked with an even year, so we can assume that this is 1 year less than 2002. So we can assume that this is 2001. So we got all this information purely from looking and being able to read and interpret our graph. So that was another really important part of our section, was being able to interpret graphs. All right, so moving on, we're going to talk about section 2.2 now. So if we're looking at section 2.2 here, we have a lot more important points than we did in section 2.1, with probably the most important point being how to calculate slope. So we calculate slope by taking the change in y and dividing that by the change in x, or if we have 2 points, it being y2 minus y1 divided by x2 minus x1. So this corresponds to having 2 points available to you, which in that case, you would have 1 point, which you would label maybe point 1, and it would be x1 and y1, and then point 2, which would be x2 and y2. So you're calculating the slope between 2 different points, and that's where that y2, y1, x2, x1 comes from. Now we have that the slope of a horizontal line is 0. So if we have a graph and our line is going across like this, it's horizontal, we know that slope is 0. And the graph of a horizontal line, it also can be written as y is equal to k, where k is a constant. So if y would be equal to 3, we would have a horizontal line at y equals 3. In this case, this would also be the y-intercept. So your graph of your equation would be the same thing as the graph of your intercept, or just labeling your intercept. All right, so in moving on, we have the slope of a vertical line is undefined. So while the slope of the horizontal line is 0, so it'd be 0, a vertical line is undefined. And that's because you can't calculate the slope at all, since technically it's going to infinity above the x-axis and negative infinity below the x-axis. So there's really no way of actually telling what that slope is. So we say that the graph of a vertical line is the same thing as saying x equal to k, where k is a constant. Also, this can be known as just the same thing as saying the x-intercept, except now there's a line instead of a point. Then we have our slope-intercept form, and this is ways that we write equations. So in this case, we would have y is equal to m times x plus b, where m is your slope, and b would be considered your y-intercept. Then also getting into parallel and perpendicular lines. Parallel lines will always have the same slope, while perpendicular lines will have slopes where the product of both of them is equal to -1. So that means that if you have two equations, two slopes, if you multiply the slopes together, they'll equal -1. This is also called having a negative reciprocal. So one of the slopes will have the negative reciprocal of the other. This means that if you have one equation where the slope is 4 and your other equation is -1/4, that would be your negative reciprocal because you're adding that negative and then you're switching your numerator and denominator. All right, then we have our point slope form, which is just another form of equations that we use. So in point slope form, you would use this equation if you were given a slope and the point. And then when you had slope intercept form, you could write that out if you had your y-intercept and a slope. So it gives you kind of an idea of what equation you need to write out in its name. So for a point slope form, we have y minus y1 is equal to m times x minus x1, where x1 and y1 is a point on the line. This point is not always the y-intercept, so sometimes you're just given any old point, and so you can use them in that case. And once again, m is the slope. Then we have our standard or general form. So you'll see it be written as standard form, and sometimes see it written as general form. They mean the same thing. It just means that your equation will be written in the form of a times x plus b times y is equal to c. We have a, b, and c are all constants. And we saw our standard form in one of our examples that we just had from section 2.1. All right, so we want to do example 5 here. So we're finding the slope, if it exists, of the line containing the pair of points. Now it says if it exists because if you find that it's undefined, it technically doesn't exist. So we want to find the slope to see maybe it's 0, maybe it's undefined, or it's an actual number. So we have 2 points here, and all we need to do is find the slope. So this is when our equation for slope is going to come in handy. So we know that slope is equal to our change in y divided by our change in x. Make it easy on ourselves. Let's just label our first and second points now. So let's say 1, 4 is our first point. So this is x1 and y1. And 8, 10 is going to be our second point. So this will be x2, y2. So now I have them labeled. And we know that the change in y is signified as y2 minus y1. And our change in x is signified by x2 minus x1. So if we pick y2, it's going to be 10 minus y1, which is 4, divided by x2, which is 8, minus x1, which is 1. And this is going to give us 10 minus 4 is going to be 6. 8 minus 1 is going to be 7. So we get 6/7. So we know the slope between these 2 points is 6/7. All right, then example 6, we want to find the slope and the y-intercept of the line. And I didn't write the line. So let me write that now. I conveniently forgot about it. It was 4x is equal to 8y plus 12. All right, so we want to find the slope and the y-intercept of this line. So in order to do this, the easiest way we can do this, because we see that this equation here is not quite in standard form, it's not quite in slope-intercept form, and it's definitely not in point-slope form. So the easiest way to calculate a problem like this is to just rewrite it in slope-intercept form. Since all we need is the slope and the y-intercept of this line, and we know that slope-intercept form gives us that. So let's just put in slope-intercept form. We know that slope-intercept form is just y is equal to mx plus b. So we want to rearrange this equation. So we're given 4x is equal to 8y plus 12. So let's isolate y. So we're going to subtract 12 on both sides. And now I'm just going to flip the equation. So I'm going to write 8y first is equal to 4x minus 12. Now all we have to do is divide each term by 8. So if we do that, I'm going to take the rest of our problem up here. We're going to get y is equal to 4 divided by 8, which is 1/2, x minus 12 divided by 8, which is the same thing as saying 3 divided by 2, 1/2. So in this case, we see that our slope is 1/2, and our y-intercept is b. So this means that b is equal to -3/2, or that our y-intercept is equal to -3/2. All right, so we found the slope and the y-intercept of that line. Now we can go on to example 7 here, which is a word problem this time. So we have if 50 books are produced at a cost of $200 and 200 books are produced at a cost of $4,700, then what is the cost per book? So how we're going to do this problem is that we're essentially going to create 2 points. So let's create 2 points. So let's say our first point, also before this, I'm going to let x be our number of books. And y is going to be the cost. Cost of production, there we go. All right, so we're gonna create our 2 points. With x being the number of books and y being the cost of production, think about our first point. If 50 books are produced at a cost of $200, our first point here is going to be 50, 200. And this will be x1, y1. And let's create our second point. So we have 200 books are produced at a cost of $4,700, some expensive books. So we're going to have 200 and 4,700, and this will be x2 and y2. So we have our 2 points. We want to find the cost per book, and if we're thinking about per book, this means that we are going to be essentially finding the average value that if we multiply by any number of books, it should give us around the right answer. So, and we have now created an equation with 2 points, so we can kind of guess where this is going. If we have 2 points, well, let's find the slope. So we have slope is going to be equal to our change in y divided by our change in x. So in this case, we're going to have y2 minus y1 divided by x2 minus x1. So we're going to have 4,700 minus 200 divided by 200 minus 50. And that is going to give us 4,500 divided by 150. Now we can divide these evenly, and that gives us 30. So we can say that the cost per book is $30. So we see that if this were an equation on a graph, then the line that would go through both of these points would have a slope of 30. All right, moving on to our example 8 here, we have that we want to find the equation of the line that passes through -1, 5, but is also perpendicular to the line containing -1, 3, and 2, 4. So what we're going to do here is that we want to find the equation of this line that passes through a point. That's our ultimate goal. But we also have another key factor here, and that it's perpendicular to a line containing these other 2 points. So the first thing we can do here is calculate the slope between these 2 points so that we can find the negative reciprocal so that we know what our slope is going to be for the line that passes through -1, 5. So let's find our slope first. So let's find our slope between -1, 3 and 2, 4. So let's say -1, 3 is our first point, so this will be x1, y1, and 2, 4 is going to be our second point, so this will be x2, y2. And we know it's y2 minus y1 divided by x2 minus x1, so this is going to be 4 minus 3 divided by, yeah, that's right, 2 minus -1. So we're going to have 4 minus 3, which is just 1, divided by 2 minus -1. That's like saying 2 plus 1. So we get 1 divided by 3. So we know that the slope of the line that contains -1, 3 and 2, 4, the slope is 1/3. This means that if our line is perpendicular, it's going to be the negative reciprocal, or it means that 1/3 times something else is going to be equal to -1. And remember we said our negative reciprocal let's write this out first, going through -1, 5. So remember with negative reciprocal, we're going to add a negative, and we're going to flip the numerator and the denominator. So in this case, it would be -3 divided by 1. 3 divided by 1 is just going to be 3. So we know that the slope of our line going through -1, 5 is -3. Now we have a slope, and we have a point, so we're going to use our point slope form. And we know our point slope form is y minus y1 is equal to m times x minus x1. So by plugging these values in, we know our point is -1, 5. We're going to say y minus 5 is equal to, I wrote that right? Yep, all right. Y minus 5 is equal to -3 times x minus -1. So once again, we have a minus -1 here, so we know this is the same thing as saying a plus. And we get y minus 5 is equal to negative 3 times x plus 1. I want to calculate this value, so let's pull this over here. And what we want to do is get our equation in our slope-intercept form, because that's what we consider to be our most simplest form. So now let's distribute our negative 3. So we still have y minus 5, but now we have negative 3x minus 3. And since we just want it in slope-intercept form, we just need to isolate y, so let's add 5 to both sides. So we end up getting y is equal to negative 3x plus 2. So our equation of the line is going to be y is equal to negative 3x plus 2, and this is going to pass through negative 1, 5. If you want to check to see if it's correct, all you need to do is plug in that point and see if the values equal each other. So if we want to check, and this is to check without graphing, because of course you can always put this in a graphing calculator or Desmos and see if it actually goes to the point. But if you just want to check algebraically, all you need to do is plug in those values. So we know our value of y was 5, our value of x was negative 1. So we have 5 is equal to negative 3 times negative 1 is just going to be 3 plus 2. And we get 5 equal to 5. So we know that this equation of the line is correct. All right. Last example of section 2.2 here is in 1990, there were 36,492 grocery stores in a certain state. In 2002, there were 40,873. For part A, we want to write an equation expressing the number y of grocery stores in terms of the number x of years after 1990. Part B, assuming that the future accuracy of the equation found in part A, predict the number of grocery stores in 2010. And C, in what year will the number of grocery stores be 50,000? For whatever reason, I left absolutely no room underneath this problem, so we're going to do all of our answers over here. So let's start with A. All you want to do is write an equation expressing the number y of grocery stores in terms of the number x of years after 1990. And it looks like we're given 2, essentially, points. So let's start by letting x equal 0 correspond to the year 1990. This means we can have a point at x equals 0 and y at 36,492. So we have 0, 36,492. And this will be x1 and y1. So if this is the case, we also have a value for 2002, which essentially would be x equals 12. Then we also get x equals 12 corresponds to 2002. And this gives us 12 and 41,873. And this will be our x2, y2. And for part A, we just want to create an equation. So we have a slope. We have our y-intercept, since we have a point that begins with 0, 36,492. That is considered our y-intercept. So all we need to do is find the slope, and then we can use our slope-intercept form. So if we want to find the slope, as always, we know it's y2 minus y1 divided by x2 minus x1, so let's plug in these values. We have 41,000 873 minus 36,492 divided by x2 minus x1, in this case, is 12 minus 0. All right, so in this case, all we need to do is calculate our slope. So we'll find that in our numerator, this is going to simplify to 5,381 divided by 12. And if you calculate that number, is going to be about 448.4. So this means that our slope is 448.4. Now we also know our y-intercept, so we're going to use slope-intercept form. Come on. So use slope-intercept form. And this way we're going to get y is equal to 448.4 times x plus 36,492. So we've now created an equation. And what we want to know for part B here is assuming that the future accuracy of the equation found in part A, so we're assuming that this equation is going to be accurate, we're going to predict the number of grocery stores in 2010. So 2010 in terms of x is going to be x equals 20. So we just need to solve y if we're going to set x equal to 20. So let's move over a little bit here and start with b. So x equals 20, 2000 and, yeah, x equals 20 corresponds to 2010. So we're just going to plug x equals 20 into our equation. So we get y is equal to 448.4 times 20 plus 36,492. So if you calculate this value, you should get 45,460. So this tells us that the number of grocery stores in 2010 is going to be 45,460 in the state that we're in. Now for our last part, part C, we want to know in what year will the number of grocery stores be 50,000? So in this case, for part C, we want to know when, so we want to know what year, so we're going to be solving for x. And we're setting grocery stores equal to 50,000. So we're going to say 50,000 is equal to 448.4 times x plus 36,492. And we're solving for x in this case. So let's subtract 36,492 from both sides. And this is going to end up giving us 13,508 equal to 448.4 times x. And then we're going to divide by 448.4. And carry this over here. If you calculate that on your own, you should end up getting 30.12. Or we say that since x is about 30, that means 30 years after 1990. So that would mean in the year 2020, we will reach 50,000 grocery stores. So we see everything in this question revolved around part A, which was finding an equation. So we use that equation, and then in part B, we wanted to find the number of grocery stores, and then in part C, we wanted to find the year. So we were solving for Y in part B, and then we're solving for X in part C. All right, that was our last problem there for section 2.2. So now moving on to our last section, section 2.3 here. And I only wrote one question just because I feel that it is the most important question in section 2.3. 2.3 really builds a lot on sections 2.2 and 2.1. So section 2.3 is really a lot of just application of what you had been doing before, with the addition of learning about residuals, and sum of residuals and the sum of the squared residuals. So the important points of section 2.3 is that you can calculate the sum of residuals to check the error between data points and a best fit line. So this means that if you have random data and you want to fit a line to make it like a prettier image, essentially, you want to create an equation that best represents your random data. So we know that a residual is calculated by y minus y hat, or in our y hat, meaning our y that we got from an equation. The best way, though, to calculate the error between data points and a best fit line is to find the sum of the squared residuals. So like we said before, that the sum of the residuals is an okay way to find error, but the sum of the squared residuals is a much better way and a much more accurate way. So always remember, the best way is the sum of the squared residuals. So we know a squared residual is just calculated by y minus y hat squared. So it's the same thing that you had before, except now it's squared. And then you do this for each one of your residuals, and then you add up all your residuals at the end. So this also tells us that a smaller sum, after you've summed up your squared residuals, a smaller sum means a better fit, while a larger sum means a worse fit. So important to keep that in mind. So for example 10 here, which is number 12 in section 2.3, we have the percentage of households using direct deposit for selected years is in the following table. So we have a table here, we have years, and it's a certain selection of years. It looks like every year is increasing by about 3. So we have 1995, 1998, 2001, 2004, and 2007. Then we have our percentage of households. So we see here that in 1995, 53% of households used direct deposit, 67% in 1998, 71% in 2001, 75% in 2004, and 80% in 2007. Now we're going to let x equal 5 correspond to the year 1995. This also means that x equals 0 corresponds to the year 1990. So we have two equations here that model the data, and they are y is equal to 2.1x plus 47, and y is equal to 2.8x plus 44. So for part A, we're going to find the residuals and their sum. Then for part B, we're going to find the sum of our squared residuals. Then for part C, we're going to decide which equation is a better fit based on what we just talked about. So for part A, what we're doing here is calculating these residuals based on our equation. So we see we have the actual data points here on the left-hand side. We have 5, 53, 8, 67, 11, 71, 14, 75, and 17, 80. And these numbers correspond to the actual years. So now what we're doing, and our M1 means model 1, or equation 1, and that's going to be y equals 2.1x plus 47. So I'm going to say model 1, or M1. And our second equation is going to be model 2, or M2. All right, so the x values are always going to stay the same. You're going to use the exact same x values, and you're computing y. So, and I forgot my little hat here on my y1, so y1 hat. Oh, and I also forgot it over here, y2 hat. we know that our data point represents x, y. So that's our original y, and then the y values that we find from our equations will give us y1 hat and y2 hat. So, for example, over here, if we want to calculate this very first value of M1, we have 5 and 53. So we're using our x value, plugging it into our equation. We know our equation is 2.1x plus 47, and we know x is 5. So we're going to say y is equal to 2.1 times 5 plus 47. And when we calculate this, we're going to get y is equal to 57.5. And that's for our very first example here in our Model 1 point. So when x equals 5, y is 57.5. And that's how we're going to calculate every one of these values. Now, if we go on to x equals 8, I strongly encourage you to pause the video after every time we do this and calculate this number on your own. So by using our very first equation, plugging in x equals 8, we're going to get 8 and 63.8 from our first model. Then moving on to x equals 11, we're going to get 11 and 70.1. Then moving on to 14, we get 14 and 76.4. Then for our last value, 17, we get 17 and 82.7. So we calculated our points. Now we can find each residual. So remember, there's a residual for every data point. What we're doing is we're going to end up summing them together. So, like we said before, all we need to do is subtract y hat 1 or y1 hat from y. So we're doing 53 minus 57.5. And that is going to give us negative 4.5. And you want to keep the negatives and positives in this case. So then our next value here, we're taking 67 minus 63.8. And that's going to give us a positive 3.2. Then we're going to take 71 and subtract 70.1. This will give us positive 0.9. Then for x equals 14 here, we're going to take 75 and subtract 76.4. So that's going to give us a negative 1.4. And for that last value there, we're going to take 80 and subtract 82.7. And this will give us a negative 2.7. And before we sum all these up, let's do our second model so we can sum up our residuals at the same time. So moving on to our second model, but of course you can always do this in whatever order you would like. For our second model, we're going to do the same thing. So this was model 1. And for model 2, yeah, I'll write those so they make a little more sense. So for model 2 here, we're going to have y hat 2 is equal to, and our equation was 2.8 times x plus 44. So 2.8, we're going to stick with 5 plus 44. And this is going to give us an even 58. So filling in here on our model 2 point, we're going to say 5, 58. Once again, I strongly encourage you to pause the video and calculate all these values on your own. Then we see our second value here, corresponding to x equals 8. We get 66.4. Then for x corresponding to 11, we get 74.8. For x corresponding to 14, we get 83.2. Then for x corresponding to 17, we get 91.6. So now let's calculate our residuals. So this is that y minus y2 hat. So for our very first case, we're going to take 53 minus 58. This is going to give us a negative 5. So that one was pretty easy. Moving on to our second one, we're going to take 67 and subtract 66.4. That's going to give us a positive 0.6. Then for x corresponding to 11, we're going to take 71 minus 74.8. That's going to give us a negative 3.8. Then we're going to take 75 and subtract 83.2, corresponding to x equals 14. And that is going to give us negative 8.2. Then we can take our value of 17, or x corresponding to 17, and we will subtract 91.6 from 80. That will give us negative 11.6. All right, so we found all of our residuals, and now we want to sum our residuals. So all we're going to do is add up all of our values here. So we see we have positive and negative values, so we're going to add them all up. So if you do this, then we will end up getting our values of negative 4.5, corresponding to our model 1, and a negative 28, corresponding to our model 2. So we see that our M1, our sum of residuals, is definitely smaller than our model 2 sum of residuals, but we know that the real test is going to sum the squares of the residuals. So part A, all we need to do was find the residuals and their sum, so we did that. Now for B, we're going to find the sum of the squared residuals. And for B here, we can't just square negative 4.5 and negative 28. We have to square each individual residual so that we get a positive value for every number that we have. So for our model 1, sum of squared residuals, it's basically the same thing, now we're just squaring. So that very first value there, negative 4.5, we're going to say negative 4.5 squared. That is going to give us 20.25. Then we're going to take 3.2 squared, and that is going to give us 10.24. Then we'll take positive 0.9 squared, and that is going to give us 0.81. Then we're going to take our negative 1.4 squared. That is going to give us 1.96. Then we're going to take negative 2.7 squared. That value is going to give us, my cat just jumped into my lap. So, sorry, got a little distracted there. So we take negative 2.7 squared, which is going to be 7.29. All right, so let's save our summing for the very end. So let's square our residuals for our Model 2 now. So starting with negative 5, taking negative 5 squared, and that's just going to be 25. Then we're going to take 0.6 squared. That will give us 0.36. And we're going to take negative 3.8 squared. That's going to give us 14.44. Then we're going to take negative 8.2 squared. Yeah. And that's going to give us 67.24. And lastly, we're going to take negative 11.6 squared. That value is going to be 134.56. So now you want to add all of these residuals up. And if you do, you should end up getting 40.55 and 241.6. So remember what we said earlier, where a smaller sum means a better fit and a larger sum means a worse fit. We have a very clear winner, Model 1 at 40.55 versus Model 2 at 241.6. So for part C, we want to decide which equation is a better fit. So we can say Model 1 equation, which was y is equal to 2.1 times x plus 47, is a better fit because its sum of squared residuals is smaller than that of Model 2. All right. So we've calculated all these residuals, and we've decided that Model 1 was a better fit, or a better equation for a better fit of our data. All right, so that concludes our review. Do not forget that today as well you have a quiz to complete that will be also on sections 2.1, 2.2, 2.3, so chapter 2. Your quiz will basically be like a taste of what your test is going to be. There'll only be a few questions on your quiz, but it'll be pretty similar to the ones that you'll see on your test. I also have office hours on Thursday, so if you decide that you want to take your test later in the day, because you have the entire day to take your test as well as your quiz, so you can choose to take your quiz and test anytime you'd like. My office hours will be on Thursday, so if you have any questions that you want to ask maybe right before you take your test, you can feel free to do that as well. And also don't forget that I will be posting our section in our next chapter, chapter 4, also on the day of the test, so don't forget to do that as well. All right, so if you have any questions or anything along those lines, please don't hesitate to email me or send me any questions or anything like that. And good luck studying for your test.